a Python library, which is being developed at the data analysis unit at the SRF together with the team of Karsten Detlefs. And it is for the analysis of dark field X-ray microscopy data. So the objective of Darfix is to provide a user-friendly package to generate maps, like the Musicity or Strain maps that you've seen from previous speakers. So Darfix can be structured in 3 different parts. The first part would be the selection of the data. Darfix analyzes images taken at different motor positions. These images are then form a 3-dimensional matrix or stack of images, which can be reshaped depending on the moving motors. After that, we have the pre-analysis part with techniques like region of interest, noise removal, and shift correction. And finally, we have the most interesting part, which is the specific analysis of the dark field microscopy data with techniques like rocking curve imaging, Musicity maps, and blind source separation. I'd just like to add that at the end of the talk, I will give a short demonstration of how this last part is done in Darfix. So here you can see an example of the graphical user interface in Darfix. As you can observe, the different models are chained together to create a workflow. This workflow is done on top of the platform Orange, which is the one that lets link every one of the different models. So yeah, same as Darfix, here we have the data selection part. After that, we have the pre-analysis widgets. And finally, the dark field X-ray microscopy widgets. So I'll just start talking about the pre-analysis widgets because the data selection is very simple. For this, we have 4 different widgets, which are the dimension definition, region of interest, noise removal, and shift correction. I'm sure most of you are already familiar with the region of interest and noise removal part. So I won't go into details there. Just say that in the noise removal part, we do techniques like background subtraction, hot pixel removal, and threshold removal. So I'll just show you the other 2. Here, what you can see is the dimension definition widget, which basically lets the user add the different motors that are moving through the data set. This can either be done manually or automatically by clicking this Find Dimensions button. Then by clicking this button, what Darfix does is just read the metadata of the files and find out which are the motors that are moving. After that, the user can, of course, change everything and just fit the data to make sure that the motors make sense. In this case, the data set that I'm analyzing is a strain scan with motors DFY and OB pitch, and with size 31 and 31, which means I think 961 images of 2000 by 2000. So continuing with this same data set, we have the shift correction part. Why do we do this widget? Basically, because at some data set we have some imperfections in the mechanical alignment, which leads to linear shift through the data set. This shift can easily be corrected, and is this done by means of this widget. So basically, in the left, you can see the widget, which is Silex-based widget. Silex is a scientific library that we are also developing at the data analysis unit. And basically, to correct the shift, the user just has to enter horizontal and vertical shift, or let Darfix find which is the optimal shift. Here you can see how the shift is useful, because on the left image, you see a sum of the stack of images before the shift is applied. And on the right image, the same sum after the shift correction. And as you can see, the image is much more sharp and better for later analysis. Okay, so back to the example workflow. We are now at the dark field microscopy analysis widgets. And for this, I would like to do the demonstration. So I'll just go to another workflow. This is live, and I'm connected to the ESRF machine. So I hope it will work well. First of all, I will just show you the dimension definition of this data set. This is a different data set that before is the Musicity scan with motors DFY and Chi. And I go directly now to the rocking curves widget. So here we see different plots. I'll just start talking about the top left one, which is basically the stack of images. You can move through it and see the different images of the stack. After that, you can click on different parts of the image on different pixels and see how the rocking curve changes on the right. As you can see, now we have a lot of peaks. That's because we are using all the stack of images, but we can easily filter by dimensions, and then just a single peak appears depending on the pixel that we are looking at. Of course, then we can change the dimension and other images will appear, same as the different values of the motor. So after looking a bit at the rocking curve, which the blue one is the original rocking curve and the red one is the fitted one by means of a Gaussian function. So after that, we can just fit all the data. Depending on the dimension, the fitting will be done in one direction or another. And just see 3 different maps. The first one, which are at the bottom of the widget, is the integrated intensity map. After that, we have the full width half maximum map and the peak position map. So that is all for the rocking curve widget. I'll just go to the next one, which is the grain plot. So the grain plot widget, as the name suggests, just shows different maps like this one that you can change here. I'll just start by the center of mass map. So the center of map looks at the intensity as a function of a motor position and uses the intensity values of the images as a statistical weight. That's why we have 2 different maps, one for each motor, the phi-y on the left, chi on the right. After that, if we don't want to generate the rocking curves like we did at the other widget, we can calculate statistical measures like full width half maximum, this without the fit, skewness, and kurtosis. And after that, we have the Musicity map. The Musicity map basically correlates the center of mass of both motors into a single RGB image, which is this one. It can be read with help of the orientation distribution map, which I'm sure most of you or some of you are already familiar with them. To show you better this, I will go back for a moment at the presentation and show you this slide. So at the left, we have the same Musicity map, and on the right, the orientation distribution. And as you can see, we can just compare the different colors on the grains in the Musicity map with the angle values of the color map on the right. And back again to the presentation, we have the last widget. So the branch source separation widget analyzes, finds the components that represent the data set. These components are actually images, and the idea is to see if the data set can be decomposed into images and see what these images are. To do this, we have we use several methods, which are principal component analysis, non-negative independent component analysis, and non-negative matrix factorization. In this case, what I did is just compute 14 components using the non-negative independent component analysis method. And what I found for this data set is this. So as you can see, the analysis is capable of finding different grains or subgrains of the scan. And on the right, the color map appears, which can then help understand how the component is in the data set. Okay, so that would be all for the demonstration. I just want to also add that even though the importance of Darfix is through the graphical user interface, there's also the possibility to be imported as a library for those more experienced in programming. Here you just have an example of a Jupyter notebook that it's actually a tutorial that you can find on my GitLab repository. And here, well, it's a part of the example where you have the region of interest and the background subtraction. It's just that you know it's possible. So all my code is open source and can be downloaded in GitLab. And also just to add that we are currently working in a paper, which we hope to be published this year. So that would be all. Thanks a lot for listening. And if you have any questions, please ask.
Thank you, Julia. So I see already we have Hugh looking to ask a question.
Yeah, Julia, this is absolutely incredible. And I think I can say for anybody who's ever had to wade through my terribly hacked together MATLAB scripts, this is, yeah, I mean, the amount of time this is going to save everybody, myself included, it's just amazing. You've really done, by the look of it, a fantastic job, and I can't wait to to test it out. That wasn't a question, but my question is actually about the registration correction or the shift correction.
Yeah.
And I was wondering if you, if you're just correcting the the systematic shifts, or if this is random shifts that you're correcting for, or both, and by what method do you do that? Because I mean, I've always found this is kind of one of the hardest or the most difficult things in the data analysis, as I guess the previous speaker can attest to.
Yeah, it's actually the linear shift. So what I look is just how the shift evolves through the data set. To find it, basically, well, I tested several different methods because as performance evolves, also time takes more. So what I ended up doing is just do an easy shift between the first part of the dataset and the second part, and then update it to find the optimal shift between those two. So basically, I just sum the first part of the image of the dataset and the second part, find the shift, and then update it by changing some parameters, which it works very well and it's very fast.
It's amazing. Well done.
Yeah, thanks.
Thank you. Yeah, I echo Hugh's sentiment that I think this is the tool that is necessary to move dark field X-ray microscopy from a niche prototype technique to a widely applied measurement method. So I'm going to go straight to Mustafa Can, because I have a feeling Inokenti's question might provoke some further discussion. So Mustafa Can, go ahead.
Okay, I will have a really short question. Thanks for the really nice talk, by the way, and I agree with both you and feel that this would probably create quite a paradigm shift for the technique. So my question is on the geometry definition. So in that particular model, you, as I understand, you define your the motors that you're moving, right? And
Yeah.
and their step sizes. My question is it possible to define a pseudo motor that represents a movement of two different motors? Because in these rock and roll scans and the Musicity scans, to do a proper to go to the proper rolling angle, you need to move both chi and phi motors in the current setup, and also d phi y actually. So you need to do such a correction of these three different motors to reach the proper what we call chi rotation right now, but raw rotation. I'm just asking whether is that possible to do?
When you mean pseudo motors, you mean the step size is the same for both?
No. So so what I mean is that for this pseudo motor, that would have a fixed step size,
Yeah.
but in the sub motors that define the pseudo motor, that would have different sub step sizes, let's say. So the overall number of steps is the same, but yeah, the each step size for these the pseudo motors would be different. Could that be possible somehow?
I don't know if it's the same as I will tell now, but we are working in adding a 3-dimensional motors. So adding more motors, it's possible. I don't know if it's the same, but the idea is to be able to do the analysis with more than 2 motors, and also with 1 motor is possible. But if the size is okay with the whole data set, then it shouldn't be a problem. But maybe we should add an intermediate step to link those motors for the maps. You wanted to say something, Jan?
Yeah, it's just, I think currently it's just not there, but we're working on increasing the dimensions, and pseudo motors can be then calculated and given as an option. But at the moment it's not included. But I mean, the structure itself, as far as I know, of Darfix allows for it. So
yes, exactly.
Just one comment. You can always use the Python interface directly and not go through the graphical user interface. And in that case, you can calculate a pseudo motor as function of several motor positions and use that as a plot coordinate instead of, as it is proposed in the graphical user interface, a real hardware motor. Another possibility would be to calculate that pseudo motor position directly in the data acquisition and store it in the list of motors, and then you have direct access to that, but that's not implemented either yet.
Okay, well, that would actually simplify the problem a lot faster, but I can also see all the challenges that can come to define something like this in spec. Yes. But yeah, thanks.
Yeah, you of all people know those. So then we have our final question comes from Inokenti. It's not exactly on data analysis, but still relevant. Would the increased coherence of the new source improve your results, or is it limited by the lens performance? And what about plastic lenses with no grain boundaries inside?
Wait.
I don't think that's a question for Julia.
Yeah, I think this might not be for you. I think this is maybe.
Well,
yeah.
she can try to answer it anyway. So.
Well, yes, go ahead, Julia.
So, what do you mean by results? So, when you talk about results, do you talk about the Musicity map, or because at the end what I'm just providing is different maps that can be analyzed. So of course it will improve the late analysis for the scientists, but in my case I don't know if that would be better.
Julia, that was for another session.
Yeah,
right.
was it? Okay.
Yeah. Actually, Mats can answer the question actually.
Okay. Yeah, I see. It somehow came back. Okay.
Yes, Mats can answer the question because that is directly relevant to the fluid tachography analysis that he has done.
I think this was an old question that we didn't have time for. Let's see if I can find it. So the coherence is already so good that I can't really see it anywhere. to me, it seems like the spot size is not really critical for the stuff I was doing.
Yes, but you do see a difference, notable difference in the images between the beam as it comes out of the machine and the beam if you put in a decoherer. What we do see is that the fine structure of the lenses gets averaged out in the image that we detect, and it just produces a homogeneous background. Now, going from the old DSRF, the old machine, to the one that we have now, the EBS machine, is like removing a horizontal decoherer. And we observe exactly that effect, that now we observe a lot more fine structure, which we interpret as artifacts from imperfections in the lens, or in some cases artifacts from imperfections in the upstream optics, which before the upgrade we did not observe because they were smeared out by the large horizontal source size and the large horizontal source divergence. With the plastic lenses, as Mats has also pointed out in his presentation already, there are no grain boundaries, but there are quite a lot of long wavelength aberrations, and those should be possible to fit and potentially remove with the Fourier tychography algorithms if they work perfectly, and in particular if the data acquisition, the tracking of all the 6 motors works perfectly. Does that answer the question?
I would say that answers the question. So I think with that, thank you once again, Julia.
Welcome.
And sorry to put you on the spot with a question that was not even yours. So I think then that brings us then to the end of the workshop. And so for the last word, I believe we're going to Harold.